Assalamualaikum and good morning. So today we're going to present about photoelectrochemistry. But first of all, let me introduce my group member, Nur Anis Zulaika binti Zainuddin, Nur Izanti binti Sahimin, Ana Zuhaili Muhammad Jeffrey, Nur Syafiqah Izwana binti Muhammad Zahari, Fatin Syafimi binti Zainuddin, and Nur Hamizah binti Abdul Hadi. So this is our contents for this presentation. So I will begin my presentation with photoelectrochemistry properties of semiconductor. The photoelectrochemical properties of semiconductor electrolyte is important for the generation of current following the exposure of electromagnetic radiation. These properties of semiconductor can be differentiated with other metals, electrodes, by understanding the band structure. For the metals, the conduction and valence bands overlap, so the conduction band can be readily occupied. For insulator, the band gap is sufficiently large. The electron cannot be promoted from the valence band to the conduction band. However, for the semiconductor, the band gap is not as large and electrons can be moved into the conduction. Here we can see the band structure of the metals and semiconductor, which is we can see that metal it's overlap, so it is readily occupied. Meanwhile, the semiconductor we have a band gaps which it can enable, which enable it to conduct or to be an insulator. So here is the hole when the semiconductor release the electrons to be a conductor, and it will, the valence orbital will become positive. So I will pass my next presentation to Fatin Syafimi.
I will continue the presentation. Now I will explain about the types of semiconductor electrode. There is a two type of semiconductor electrode, which is N-type and P-type. For the first one, I will explain about the N-type electrode. For the N-type electrode, it has a small amount of pentavalent impurity is added to a pure semiconductor, providing a large number of free electrons. As you can see from the diagram, is a bonding of the silicon and the phosphorus, which have a 4 covalent bond and 1 free electron, which is said to be the pentavalent impurity. These electrons are the excess of free electron with regard to the number of free electrons required to fill the covalent bonds. The addition of the pentavalent impurities such as arsenic and antimony provides just a large number of free electrons in the semiconductor crystal. It also known as the donor impurity due to the each atom of them donates 1 free electron crystal. This is also the band gap theory for the N-type electron. As you can see, the Fermi level is near to the conduction band compared to the valence band. Okay, this is the diagram of the N-type electrode. The large number of free electrons are available in the conduction band because of the addition of the pentavalent impurities. So in the conduction band, you will have the excess of electron due to pentavalent impurity. These electrons are free electrons that did not fit in the covalent bonds of the crystal. However, a minute quantity of free electron is available in the conduction band, which forming whole electron pairs. The important points in the N-type electrode is the addition of the pentavalent impurity result in a large number of free electrons which available in conduction bands. When the thermal energy at a room temperature is imparted to the semiconductor, a whole electron pair is generated, and as a result, a minute quantity of free electrons are available. This electron leave behind holes in the valence band, which it will form a electron hole pair. Here N stand for the negative material as the number of free electron provided by the pentavalent impurity, which it will create for the greater number of electrons compared to the number of holes. This is for the P-type electrode. P-type semiconductor is formed when a trivalent impurity is added to the pure semiconductor in a small amount, and as a result, a large number of holes are created in it. A large number of holes are provided in the semiconductor material by the addition of trivalent impurities such as gallium and indium. It also known as the acceptor impurities because each of them create one hole which can accept one electron. As you can see for this diagram, the gallium and the gallium will provide only 3 electrons, which will create a hole over here. So an example is gallium is used as an impurity atom which have a 3 valence electron. So added to the germanium crystal, which have a 4 valence electron. So obviously it form 3 covalent bond due to the availability of valence electron with gallium. So the missing electron is known as a hole. Each gallium atom provide one hole in the germanium crystal. As an external small amount of gallium has a number of atoms, therefore it will provide a lot of holes in the semiconductor. Energy band diagram of the diagram P-type semiconductor. As you can see that in this diagram, there are many of holes present in the valence band. A large number of hole or vacant space are available in the valence band. A small quantity of free electron is available in the conduction bands. The produced when thermal energy at the room temperature is imparted to germanium crystal, will forming an electron hole pair, but the holes are more in the number in the valence band compared to conduction bands. It is because of the predominance of holes over electron that material is called as a p-type semiconductor. The p-type is stand for the positive materials. This is the difference between the n-type and p-type electrodes. As you can see, this is the diagram of the band gap between for the normal p-type and also the n-type semiconductor. It will show the different type of level Fermi level. The difference is for the nature of the doping element. For the p-type, you will create a vacancy of a hole, which known as a atom. For the n-type, will add the extra electron and unknown for donor atom. And the type of impurity added is for p-type trivalent, for the n-type is pentavalent. The energy level also, for n-type, the excited energy level is close to the valence band and away from the conduction band. While for the n-type, the donor energy level is close to the conduction band and away from the valence band. For the Fermi levels lies between the energy level and the valence band for the p-type, and for n-type, the Fermi levels lie between donor energy level and also the conduction bands. And lastly, for the movement of majority is a movement of the electrons is for the p-type is carry from the higher to lower potential. For the n-types, it will carry from lower to higher potentials. That's all from me. I will carry the presentation to my others member.
Next, I will explain about the Fermi level in a semiconductor. So by definition, Fermi level is the highest energy level that an electron can occupy at the absolute zero temperature. Fermi level lies between the valence band and conduction band, where electrons are all in the lowest energy state at the absolute zero temperature. So Fermi level also considered as the sea of fermions or electrons, above which no electron exists due to low energy. And the Fermi level change as solids are warm or electrons are added or withdrawn from the solid. Next. So the existence of Fermi energy level follow the Pauli's exclusion principle, which states that two fermions cannot occupy that same quantum state. So if a system has more than one fermion, each fermion has a different set of magnetic quantum numbers associated with it. Next. So the importance of Fermi level. So Fermi level is very important, especially in quantum mechanics, in determining the electrical conductivity. So some of the Fermi energy applications are it's widely used in semiconductor and also insulated and metals, where we can determine the electrical conductivity from these three types. And it also important in determining the electrical and thermal characteristics of the solids, and also important in nuclear physics to understand the stability of white dwarf. Next. So this is a diagram of the semiconductor, for example, where the Fermi level lies between the conduction band and the valence band. So the space between conduction band and valence band is the forbidden gap. So EF is the Fermi energy. Next. Okay. So the position of Fermi level. So the position of Fermi level is always fixed the charge carrier concentration, which is the free electrons, and defect ionization in semiconductor. However, as the environment factors change, so it may affect the position of Fermi level. So there are two important factors that affect the position of Fermi level, which is the nature and concentration of the impurity in the semiconductor. So as we introduce the donor impurity to the system, it will shift the Fermi level up, while introduction of an accepted impurity will move the Fermi level down. Okay, next. So, and second factor is the temperature. So as the temperature change, it will affect the Fermi level between the conduction band and the valence band. So first, at low temperature, so Fermi level is in the middle of the forbidden gap between the conduction band and the donor level. So as the temperature increase, so Fermi level will shift down. So the greater the X, which means the concentration of the neutral or charged donor. So it depends. So the greater the X is, the slower it moves. So which means that as the concentration of the neutral or charged donors increase, the Fermi level will move down slowly or move upwards. So it depends on temperature. So at the right side is the example of equations, how the temperature will affect the movement of Fermi level. So I want to show you that the EF means the Fermi energy. So where the N in the equation show the electron concentration in the conduction band, while P means the whole concentration in the valence band. Next. So what happens if the temperature in the intermediate? So in the intermediate temperature, the free electron concentration is temperature independent, which means it's not really depends on the temperature. So Fermi level proved to be under the donor levels and continue to move down as the temperature grows. So this is the example of the equations where the temperature, you can see in the equation that if the temperature is increased due to we have ln n over x, so as temperature increase, the EF, total EF will be decreased. So as temperature remain higher, the Fermi level will continue to decrease. So next. Okay, so this is the summarize of 3 examples that will affect the position of Fermi levels. So for the first graph, which is the graph A, so the temperature dependence of energy level, Fermi energy under the assumption that Np equal to Nn. So for this explanation, I explain you based on the assumption that the P type are same as concentration of N, where P is the concentration of hole in the valence band and N is the concentration of electron in the conduction band. So each semiconductor or maybe insulator and metal may have different types of concentration between P and N. So for this situation, we assume that both are the same. So for the graph B, which explains the dependence of ln N over 1 over T, which is temperature. So there are 3 types of line here which correspond to the different value of X, where X is the concentration of neutral donors or charged donors. Next. Next, I will pass to our next presenter.
Okay, I'll continue with the next presentation about the photoeffect at N and P-type semiconductors. Next. So, photoeffect refers to the energy transfer from photon, which is from the electromagnetic radiation, to electron contained inside the material, which is referred to the semiconductor. So, photoeffect can be divided into two, which is external photoeffect and internal photoeffect. External photoeffect, if the electromagnetic radiation hits the surface of a solid body within the ultraviolet range or UV range, electron can absorb energy from the photon. Then they are able to overcome the required work function to escape from the solid body, which provided if there is sufficient photo energy. Next is the internal photo effect. Internal photo effect is described as absorption of electromagnetic radiation within the solid body. Electrons are lifted from the valence band inside the semiconductor to conduction band, creating electron hole pairs that will enhance the electric conductivity in solid body. Next. Okay, since the semiconductor only involve the internal photo effect, so in order for the internal photo effect to function, it requires p-n junction. How p-n junction actually works? In the addition of donors and acceptors, adjacent p and n region, as you can see at the left hand side region, created inside the semiconductor. Layers by layer growth of semiconductor enables transition within one atomic layer to the subsequent one. If p and n dope materials brought into contact, holes from p-dope side diffuse into the n-type region, and vice versa, where the n-dope side diffuse into the p-type region. So this will create the diffusion layer at the center. So the strong concentration gradient formed at the p-n junction, which is at the center. p-n junction and diffusion layer is the same thing. Diffusion occur where p region diffuse into the n region and the n region diffuse into the p region. So the number of majority carriers reduced on both sides, as you can see at the second diagram, which is the number of holes decrease from left to right, and the number of electrons decrease from right to left. So the charge attached to stationary donors or acceptors create a negative space charge on p side of the transition area and positive space charge on n side. As a result, equilibrated concentration of free charge carriers on electrical field is built up across p-n junction, creates depletion layer. So that's it for me. I'll pass to the next group members. Thank you.
So I will continue with photoelectrochemical splitting of water. So it is a process that uses semiconductor materials to convert solar energy directly to chemical energy in the form of hydrogens. So it's basically use hydrogen as an energy carrier. So this is a long-term technology pathway with the potential for low or no greenhouse gas emissions. Since it uses hydrogen as an energy carrier, so it will give benefits such as it will reduce greenhouse gas emissions, and it can reduce air pollution as well as improve energy efficiency. So the semiconductor, the process involved with the immerse of the semiconductor in the water-based electrolyte, where sunlight will energize the water splitting process. Next. Okay, so this is the basic principle of the photoelectrochemical, and this is the diagram. As we can see in this diagram, the electrochemical consists of the three main parts, which is the working electron, which is the semiconductor, or we call it as a photoanodes, and the reference electrode, which is usually made of platinum, and also the water that acts as an electrolyte. So basically, what happened is that when the light falls on the working electrode, the electron will excite and flow through the wire to the reference electrode, leaving behind the positive charge named hole. So what it actually happened is that since this photoanode is an n-type semiconductor, and we know that there is a valence band and the conduction bands, and theoretically we know that the valence band is filled with electrons and the conduction band is mostly empty. So when it's been excited with the external energy source or the direct sunlight, the electrons in the valence bands will excite to the conduction band and leaving the holes in the valence bands. So the O group through the liquids of the electrolyte will move to the surface of the electrodes and will react with the holes and associated with 4 photoelectrons and will be result in oxygen molecules. So at the reference electrode, the electron transfer will be react with the water molecule to form an hydrogen molecule. So I guess that is from me. Thank you.